All right, hi friends. So we're going to come a little bit closer into our own cosmic backyard, the Earth. So this is the Earth as I choose to look at it often, which is from below. So this is a picture of our robot I'll introduce you to in a little bit, working under the sea ice outside of McMurdo Station, which is possibly my favorite place on the planet. But for some reasons that we should care about this, in fact, getting back to Carl Sagan and how remarkable he was, I think were his thoughts on how connected humans are with the entirety of the cosmos and even with our own planet. And so I really loved some of his thinking on this subject. And here he's starting to talk about what we now refer to as Earth system science, which is the idea that the Earth and its entire population, humans, any organisms, the plants, the atmosphere, that it functions as a system and that we're all connected. And that as a part of that experience, it's our duty to protect it. And so, as Anne mentioned, some of the great work that he did was protecting people and protecting our planet. And so I'm going to tell you a little story about how thinking about space brings us closer to our own home. So this is my personal scientific hero, and this is Galileo. And so Galileo built one of, or if not the first telescopes in about 415 years ago. And if you have ever looked through a pair of binoculars, if you were to take one of those binoculars out, then you would be looking at the universe the way that he did. And what he did was remarkable. You should read his first paper, what an opener, or his first paper with a telescope. And what he did was to point it at the moon and say, my gosh, the moon is a planet. There's mountains, there's valleys, there's scarps, there's features that remind us of our own planet. He looked inward, then he looked outward. He said that there were so many stars in galaxies that you could see star clusters that had so much more happening in them, not galaxies, but clusters. And so he really looked across the entire system. And he said, now put all of that away, and I want you to focus on this thing that's happening in the outer solar system. And what he noticed were these pictures that he's drawn up here. So these are pictures from his original journal and from the publication, and I have it tattooed here on my wrist, which are the original observations of these 4 points of light moving around the disk of Jupiter, right? So for all of humankind, we had known that there were about 7 moving objects in the sky. We could see that Jupiter and Mars and Venus were different, but we couldn't see what was just around them. And so for the first time, we had these 4 points of light, and he noticed that as you watched them from night to night, the number of those objects and their positions would change. And eventually figured out there were 4, watched them move around over the course of about 3 months, and revolutionized everything we thought. And the reason for that was that at the time, the conventional wisdom was that the Earth was not only the center of our solar system, but it was the center of the universe. And with observations like these, he flipped that upside down and showed us that the Copernican version really was right. That not only was the Earth not the center of our solar system, but not the center of the universe. In fact, we're not the center of everything, perhaps something we could all be reminded of now and again. But it was an amazing observation. And so it was really, and the ability to step out there and say this really bold thing, right? It took almost 400 years for him to be forgiven by the Catholic Church. But what I find poetic about it actually is that in this system that he identified, like I said, with the very first telescope, we may have the first chance of actually seeing life beyond our home planet. And it's in worlds like this one. And so this is the one that I study the most. This is Europa. And so Europa is about the size of Earth's moon, and it has on the outside a giant ice shell that we think is somewhere between 5 and 30 kilometers thick. And I'll tell you why we think that. But when we look at Europa, it's not just what you see, but what you don't see that really matters. If you look at this picture, what is jumping out at you that's missing from every other planetary surface that you've seen? Craters. Exactly right. There are no craters. Where else are there very few craters? Or there's not none, but few. It's the Earth, right? So this planet is actually tearing itself apart, remaking its surface on roughly the same time scale that the Earth is doing that. That's truly remarkable. It has the same level of geologic activity as a planet made of rocks. In fact, what's special about Europa is this activity. Those cracks on its surface are tectonic in nature. We don't understand exactly how they work. The reddish materials you're seeing are salts. We don't really understand their chemistry. We're trying to figure out how this planet works by looking at its surface and trying to see below. And so what we've been able to identify, as I mentioned, was this ocean that's underneath it, using its magnetic field and its interaction with Jupiter. So this was explored by the spacecraft that bears Galileo's name in the late 90s and early 2000s. And so that picture from the surface now down into the interior using geophysics also told us that this planet is actually surprisingly more terrestrial than it is ocean world in some respects. You see, in the outer solar system, water is not particularly rare. There are planets mostly made of water. In Europa's case, it's this thin veneer on the outside, which functions very much like the ocean on our planet. It's directly in contact with the rock below, right? And on our planet, we know this is a source of energy, a place where life has existed and perhaps even began at the seafloor. And so when we start thinking about this planet, this distant world 5 astronomical units away, it's remarkably similar to the things we see on our own planet. And so we're trying to figure out what actually lies below. What's happening inside this ice shell? What's happening in the deep interior of Europa? Is there water inside the ice shell? How does it communicate with the surface? Are we bringing nutrients from the surface down and things from the subsurface back up? And so we're sending entire spacecraft to be able to study that. And that's some of the work that we're doing to understand the geology and the evolution of a world like Europa. And one day, where would we all like to go? Well, obviously, at least for people like me, I can't wait to get into that ocean or any liquid water we can find inside the ice shell. And so that actually kind of drove me and my team to start thinking about where we could do these kinds of experiments. And in fact, the Earth is a great place to start. This is a system we understand. It's a place we can go, and we can test the ways that we measure and think about things. So I got started thinking about Antarctica as a way to think about Europa, going to our backyard to go out into space. And in so doing, discovered this planet for the first time myself. So as I like to say, I'm new to the Earth. But this is the way I like to think about it. And so here's McMurdo Ice Shelf, which is very close to that first picture that I showed you. It's the US home base in McMurdo. This is the Ross Ice Shelf. This is a floating piece of ice made of glaciers that stitch together that's the size of France. It is planetary in scale, right? And this is Thwaites Glacier, which is a system I'll describe to you in a moment. So we started building underwater vehicles, like this robot ice fin I mentioned, in order to be able to get underneath the ice here and get ready for one day sending these things to Europa. But in the meantime, we might as well take a look at our own planet and try to understand it. And so IceFin has things like science sensors that measure the ocean. So importantly, we measure the salinity, the oxygen, and the temperature. And that actually altogether gives us a fingerprint of the water column. It tells us where the water formed, where it's going, and what it's interacted with, such as melting glaciers. So we can measure climate change in real time. We have sonars across the vehicle that allow us to map the environment. We have cameras because we're humans and we have our eyes connected to our brains. And then we build the electronics inside the vehicle so that we can know where we're going underneath the ice, move around fully in 3 dimensions, and take all of the instruments we'd normally put on a mooring on a 3-dimensional journey underneath the ice. And so what that's allowed us to do is to start targeting systems, not just because they remind us of Europa, but because they're important for the Earth. So this is Thwaites Glacier, and over the last 30 years, we've watched this glacier recede dramatically and collapse. This giant ice shelf used to be a stable feature, and now it's basically going away. And if you can see it now, it's basically a connected set of icebergs. So this massive thing is actually protecting us from a great amount of sea level rise. It's melting at what's called the grounding line, and it's forcing the thickest part of the glacier to be exposed to the warming ocean. And so as that grounding line moves back, it's a place we've never been able to take any data, but it turns out to be a place where robots are really useful. So if you want to get through 30 kilometers of ice on Europa one day, getting through almost a kilometer, 600 meters in this case of ice on Thwaites Glacier, is a nice way to start that. So what we did is to go out with our colleagues, so members of my team are in this shot, members of the BBC, members of our team from the British Antarctic Survey, colleagues from NYU and from Penn State. And this is us standing on that ice shelf, 600 meters below is the ocean. And then we deployed IceFin through the ice using this frame in the background here. So this is early 2020, before all of our lives were about to change. But this is what we were doing in January. And so what we do with IceFin is to put it down through a borehole through the ice shelf, and then allow it to kind of swim underneath. So here's the position on Thwaites that we were going. We take the robot, we put it down through the ice. One day we'd like to melt into the ice ourselves. And then we put it out underneath the glacier and start moving towards these places that we've never seen. And it allows us to measure, like I mentioned, the temperature, the salinity of the water column, the topography underneath the ice. And all of these tell us about what's happening. So what you're seeing here is kind of our walking on the moon shot, which is the very first view of a grounding line of a major glacier. And it's taken, and what you can see is, you can see this ice is full of rocks. It's been kind of ground up as it gets close here. And right here at the grounding line is the first contact of the ice, the ocean, and the glacier. And what's happening here, we can see, is significant amounts of melting. And so we can measure that in real time. And what that tells us, this is data from the vehicle, is that that warm water is making it all the way back here and eroding the glacier like we thought. So this very, very warm water, this is 2¼ degrees above the temperature at which it would be freezing. So it's a lot of heat available to melt this very cold system. But what we also discovered was that inside the cracks is an even more important story, perhaps, which is that these are the places that are melting the fastest. So you remember that picture I showed you of the glacier falling apart? Well, the melting that's happening up inside of these features, which we've never been able to measure before, is actually widening those cracks and making them more unstable. So this is a process we never knew of that we need to now think about as we try to protect our own planet and figure out how long we have to save it, right? Things that we have to do. So I just wanted to share with you that little vignette because it really is the inspiration of distant worlds that gave us the ability to measure things like this. And there's many examples of that in the Carl Sagan Institute, in planetary science and in earth science, of collaborations between people that think differently that allow us to see things for the first time. And so we're really excited, and I'll just share with you in closing that Europa Clipper launched just a few weeks ago, the first spacecraft that will actually go back and target Europa. And one of the cool things that we're doing there is sending an ice-penetrating radar that was used first in Antarctica out to Europa to be able to measure some of that ice shell that I showed you in the earlier parts of the talk. So anyway, thank you so much for allowing me to be here, and it's been a pleasure.